Hello everyone, welcome to a fourth online video. So in this, we are going to apply the fourth boundary conditions. We are going to discuss the fourth type of boundary conditions. So this type of boundary conditions will going to be applied for uniform cross-sectional rectangular fin. So in the previous videos, we will discuss about uh, three types of boundary conditions. So those are: the first boundary condition is the fin is having an infinite length. Fin is having infinite length, and the second fin is having infinite length. Second boundary conditions, fin is having finite length. Finite length. Third boundary conditions, tip of the pin is insulated. So insulated at the tip of the pin. And now in this video we are going to study about fourth boundary condition, that is convective boundary conditions in the for short fin. Convective boundary conditions for short fin, or derive the temperature distribution equation and equation for the heat transfer through a fin, which is of finite length and losses at the tip or by convection. There is a convective type of boundary conditions. So at the tip of the fin there is a convection heat transfer takes place. So you can observe this is a base, the base of the material. So this is extended surfaces, and here this is maintained at T0 temperatures. This tip of the pin is having convective mode of heat transfer, that is H A theta. This is a convective mode of heat transfer. So along this pins, conduction mode of heat transfer takes place. At this tip of the pin, convective mode of heat transfer takes place. So that's why this equation is minus K A dt by dx is equal to H into A dt. So here, as you know that the basic general equation is theta is equal to Tx minus T infinity is equal to A cos hyperbolic mx plus B sin hyperbolic mx. This is taken as equation number 1. Here x is equal to 0 and x equal to L. When x equal to 0, T of x, this T of x is equal to T naught. That is this base is maintained at a temperature of T naught. So we have to substitute these two values in the equation number 1. So we get the T naught theta naught is equal to A. If you put this x equal to 0 in this, so it becomes 1. Cos hyperbolic 0 is 1. A into sin hyperbolic 0 is 0. So 0 into B is 0. So, and if you substitute this T of x is equal to T naught. T naught minus T infinity is nothing but theta naught. So that's why theta naught is equal to A. So this is taken as equation number 2. When now second boundary conditions, this is when x equal to L, when x equal to L, so what happens here, minus Ka dt by dx at this position, say at x equal to L, this position, conduction is equal to convection. So minus Ka dt by dx is equal to Ha theta, or you can say that minus Ka dt by dx is equal to H into theta. This A and this A get cancelled here. So from this, from equation number 1, you can substitute. So we are having d theta is equal to this. So we have to differentiate this with respect to x. That then only we can able to apply this boundary condition. That is Ka dt by dx is equal to H theta. This is okay. So next minus K, differentiate this. We get that A m sin hyperbolic H sin hyperbolic mx plus B m cos hyperbolic mx. Just directly here directly substitute the value of dt by dx. So is equal to, this is equal to, this is h as it is, and this theta is equal to what, a cos hyperbolic mx plus b sin hyperbolic mx. So substitute the value of a and x is equal to L in the above equations. So that means substitute the value of a, this a, and the x is equal to L, whatever we get that this value. So substitute, we will get that minus k. A is nothing but what, theta naught. So m sin hyperbolic mx plus b m cos hyperbolic ml is equal to h into theta naught cos hyperbolic ml plus b sin hyperbolic ml. Just we can put that where there is a x, then we can put that x is equal to L. Where there is a, then we can put that theta naught. Then minus km, we can simplify this. Minus km theta naught sin hyperbolic ml plus b cos hyperbolic ml, which is equal to h theta naught cos hyperbolic ml plus b sin hyperbolic ml. So next simplify it again. Minus theta naught sin hyperbolic ml plus b cos hyperbolic ml is equal to, just like what I can do, this km will take in this side, then it becomes h by km, then is into theta naught cos hyperbolic ml plus b sin hyperbolic ml. So again we are going to simplify it by keeping simplify it by what I can do, just I can separate this p, the entire equation, just I need the value of p. So p is equal to what happens, this is as it is here, minus theta sin hyperbolic ml plus h by km divided by this value. So this is equation number 3, and dividing both the numerator and denominator by cos hyperbolic ml, then it becomes what, b is equal to minus theta naught tan hyperbolic sin hyperbolic ml by cos hyperbolic ml is tan hyperbolic ml plus h by km. So this and this get cancelled here. In the denominator, what happens here, cos hyperbolic ml is nothing but 1 plus h by km. So sin hyperbolic ml by cos hyperbolic ml is equal to tan hyperbolic ml. So again substituting the value of a and b, this and the value of a is already, we get that a is equal to theta naught. Just can substitute these two values in equation number 1. We will get that theta is equal to theta naught, a is nothing but theta naught cos hyperbolic mx is as it is, and the b is nothing but minus theta naught tan hyperbolic ml plus h by km divided by 1 plus h by km into tan hyperbolic ml. This term is as it is here, and sin hyperbolic mx. So next again we are going to simplify it. So here theta is equal to what happens, theta naught cos hyperbolic mx minus tan hyperbolic mx plus h by, so this is next theta is equal to theta naught, just I can take these two, this theta naught is common in these two terms, so I can take it outside, and in the bracket what happens here, cos hyperbolic mx minus of into bracket tan hyperbolic ml plus h by km divided by 1 plus h by km into tan hyperbolic ml into sin hyperbolic mx. So next theta by this coming this side, theta by theta naught, theta is nothing but what, t of x minus t infinity, and theta naught is nothing but what, t naught minus t infinity, which is equal to cos hyperbolic mx, so as it is minus of this as it is, and so this is our required equation for the temperature distribution. Next, for the same boundary condition, we are going to find out the heat flow. So as you know that, we know that q is equal to minus k dt by dx. It is taken as equation number 4. From equation number 1, we know that theta is equal to a cos hyperbolic mx plus b sin hyperbolic mx. So we can substitute this value. So for that we need to differentiate this theta with respect to x. Then it becomes a m sin hyperbolic mx plus bm cos hyperbolic mx. Then dt by dx at x equal to 0 is equal to am sin hyperbolic m0 bm sin cos hyperbolic m. This is become 1 and this is become 0. So it becomes d theta by dx at x equal to 0 is equal to bm. So from equation number 4, so I can substitute this value in the equation number 4. Then we get q is equal to minus ka bm, and substitute the value of b and m. So we already know that b is nothing but what, theta naught sin hyperbolic ml plus h by km divided by 1 plus h by km tan hyperbolic mm. So what happens here, q is equal to root of h p k theta naught minus t infinity into tan hyperbolic ml plus h by km divided by 1 plus h by km into tan hyperbolic. This is our heat flow equation when the tip of the fin is subjected to the convective heat transfer. So this is our fourth boundary conditions. This equation is representing the heat transfer, and that our equation is representing the temperature distributions. This is the temperature distribution equations. Okay. Now fifth boundary condition, that is heat transfer from a bar. There is one bar connected to the two heat sources at different temperatures. There is one bar, so that is connected with the two heat sources, the T1 and T2 temperature. So there is one bar. There is one bar like this. This is one bar. So at the end of this side and this side is maintaining the temperature. Suppose this side is maintaining the temperature T1 and this side is maintaining the temperature T2. So here T1 and T2. So this is our fifth boundary condition. So next what happens here? Again we know that this equation is taken as equation number 1. So x equal to 0, T of x is maintained at T1 temperature. So then theta 1 is equal to A, this is 2. And if x equal to L, that T is equal to maintained at T2. So you can substitute that x equal to L here and T of x is T2, then it becomes theta 2 is equal to A cos hyperbolic ml plus B sin hyperbolic ml. Then substituting the value of A, that is A is equal to theta known in equation number, in the above equation, that this equation, so we can get the theta 2 is equal to theta 1 cos hyperbolic ml plus B sin hyperbolic ml. Then B is, if we simplify this, then B is equal to what? Theta 2 minus theta 1 cos hyperbolic ml divided by sin hyperbolic ml. This is taken as equation number 3. Then we can substitute the value of A and B, this value and this B value, in the equation number 1. This is equation number 1. A and B value, we have to substitute that here. We get the theta is equal to T1 cos hyperbolic mx, because theta 1 cos hyperbolic mx, because A is nothing but theta 1 plus theta 2 minus theta 1. This is B as it is. So this is our required equation for the temperature distributions. Now similarly, heat flow. We know that Q is equal to minus k dt by dx at x equal to 0. This is taken as equation number 4 from equation number 1. So same, theta is equal to A cos hyperbolic mx plus B sin hyperbolic. Just we need to substitute this value. So for that we need to derive this, differentiate these equations with respect to x. Then we can get this A m sin hyperbolic m 0. So this becomes 0 and this becomes 1. Then we get that theta d theta by dx is equal to bm. Again we have to substitute this value in the equation number 4. We get that q is equal to k minus k bm. Again we have to substitute the value of b and m in the in this equation. So we can get that q is equal to root of hb by k theta 1 cos hyperbolic ml minus theta 2 divided by sin hyperbolic ml. This is what our required heat flow when the rod is subjecting to different temperatures. Subjecting to the two different temperatures. Okay, thank you. Please watch all videos. Thank you.